So the next signal we're going to look at is the continuous time impulse function, or the Dirac delta function. So it's named after Paul Dirac, who was a French mathematician and physicist, I guess. It's a bit more complicated to think about than the discrete time Kronecker delta function. So this presentation is going to be a little bit longer than our standard presentation so far. So what we want to do is be able to explain essentially how the Dirac delta function works and be able to use it. We have that sampling property for Kronecker deltas. We also have this sampling or sifting property, it's sometimes called, for continuous time delta functions. And then we can use impulse trains in the same way. We can use those as a mathematical model for how we sample signals. So let's look at the unit impulse function. So there's many ways to interpret the unit impulse function. It's actually not a function. It's called a distribution or a generalized function, but we're not going to really delve into some of the mathematical subtleties. We're going to try and give an intuitive definition which should work for most of our applications in this class that we're going to see. So in that type of interpretation, we think of the delta function as having a unit area concentrated at time equals 0. Delta of t is a unit area concentrated at time equals to 0. So what does that mean? So what you should think about when you see the unit impulse function is that it has an area under the curve of 1 entirely concentrated at 0. But this really only makes sense if you're essentially integrating the delta function itself or integrating the delta function times another function. So when you see delta of t, you should ask yourself two questions, like, is something being sampled here or is something being copied here? And we'll see these two interpretations next. So you can shift delta functions, and you can multiply the delta function by a constant. So if I wanted to shift it, for example, I want to take delta of t minus a third. That just shifts it over to again, much like the Kronecker delta. You're asking is, when is t minus a third equal to 0? And so that's exactly at t equals a third. So here we have a third here. If you want to multiply by constant alpha, then you're going to essentially make that unit area equal to an area alpha. And so alpha can be, of course, greater than 1 or less than 1. It can also be negative if you want to think about the delta function going below the axis. So what we want to look at now is the sampling property, or the sifting property of the delta function. And it looks very much like it does in discrete time. We have this, instead of the summation, we have an integral here. And what we do is what we have is the same sort of thing. We have the function itself, and then we have a delta function centered at t equals tau. And then we say, the value of the function at time tau is just equal to this integral. And so what we have plotted here, this is of course our delta function for tau equals 1. And here's this is x of t is equal to this. And when I take the product of these two things, this is x of t times delta of t minus 1, right? And so we can see here, this is exactly this. So basically, it's going to pick up the value. This part here is just x of 1. So it's x of 1 times the impulse function centered at that 1. So now the area under the curve is equal to exactly 0.5 or 1/2 e to the minus half. And so when you integrate this area, this unit area, over all from minus infinity to infinity, you get exactly x of tau, or x of 1 in this case. So how do we think about the delta function? Well, we can think about it intuitively as a limit of rectangles. So we can think of, we want to have a unit area centered at, squished in all the way just only at time 0. So we can think of the rect function, and we can squish it and squish it and squish it, but as we squish it, we make it taller and taller and taller, so that we maintain it having a unit area under the rectangle, but it's getting, thinner and taller and thinner and taller. So we can see how this looks. There's a rect function, there's, we squished it by a factor of, I think, 4 here, so it's by 2 rather. We made it squish it by a factor of 2, so it got twice as tall. So now this is of total width a half and height 2, so the area is still 1. Now it's total width a fourth and the height is 4, so it's still area 1. And now it's 8, so it's width 8 times a height of 8, so that's still equal to 1, and so on and so forth. You take the limit of all those, getting taller and taller rectangles, but narrower and narrower, you get exactly the delta function. So that's what we mean by being a generalized function. It actually exists as the limit of this collection of functions as you kind of let this epsilon factor, this kind of width factor, go to 0. And so the height is blowing off to infinity. It's also equal to the limit of all sorts of other functions. So nothing special about rectangles here, but it's helpful to think about the rectangles because it's an easy picture to see it as a limit of these rectangles as they get narrower and narrower. So how does time scaling then affect the delta function? So that's a little bit more complicated. So if we can get a feeling for it by looking at the previous limit of rectangles. So remember we had shifting was okay. You could shift a delta function. Delta of t minus 5 is an impulse centered at 5. But here when you do the scaling, you might be changing the width of the box, so you might be changing the area under the curve. So if we replace the rectangle function with rect of at, then the rectangle that we have in this new rect function is of height 1, but width 1 over a. So the total area is actually just 1 over absolute value of a. So if we take the limit, then we can see that delta of at is actually 1 over a delta of t. So it's 1 over magnitude of a delta of t. So this stretching or squishing factor kind of stretches or squishes the area correspondingly. So if we extend this, we can say delta of at minus b is equal to 1 over magnitude of a delta of t minus b over a. So you can do shifts and squishes much like we did with regular functions. You can do that with the delta function as well. You just have to remember that you're going to be carrying around this multiplicative factor because we're dealing with this unit area under the curve. So here's an example. So let's use the unit sampling property of the impulse function to evaluate the integral 1/2 e to the minus t over 2 u of t, so it's basically the same function we were looking at before, except now it's multiplied by u of t, times delta of t over 4 minus 2. So we have both a scaling and a shift in our delta function. So the first step to do is we don't want to have this t over 4 business lying around. It's really super annoying to deal with. We want to know where is the delta function, right? And the delta function in this case is at 8. When t is equal to 8, the thing inside the delta is equal to 0. So that's where that's where the spike is. That's where the impulse is. So first you rewrite the delta function in terms of to get it as 4 delta of t minus 8. That's 4 is coming from 1 over 4. Then, of course, we apply the window to the signal. That's the next thing we want to do. So instead of having an integral from t equals minus infinity to 0, this u of t makes it have an integral from 0 to infinity, because this thing is u of t is only equal to 0, or is only equal to 1 when t is bigger than 1. And then we can use the sampling property to say, okay, well, what is this? So what is this at t is equal to 8, right? So then that's the third step, and so then we can solve this problem. So, it looks a little complicated at first, but really just follow this recipe and you can get the answer. So we had impulse trains in discrete time. We also have impulse trains in continuous time. So here again, now we have evenly spaced delta functions now at integer multiples of t0. So that's the sampling interval here. I think t0 is 1/4. So t0 is equal to 1/4. So every 1/4 we get a delta function. So it's the same kind of impulse functions as we saw in discrete time. So what's useful about impulse trains? Well, we can use them to model a sampled signal. So if I look at x of t times this impulse train, then what I'm going to get at the output is I'm just going to be evaluating x at those points in the impulse train, so at integer multiples of kt0, and then I'm getting this delta of kt0. So this looks a lot like if I converted these deltas into kind of delta of k in the discrete time, Kronecker, then I would essentially get exactly my sampled signal in discrete time as a discrete time signal. So that's why these are very useful to these impulse trains are very useful for thinking about the connections between continuous time and discrete time. So let's see how this looks. So if I took this signal, this red signal, it's got a slightly complicated functional form, but whatever, and I multiply it by this impulse train, then what am I going to get? Well, I'm just going to pick up the value of the signal at those points where the impulses are. So I'm going to get something that looks like this. So this is just the sampled version of the signal, but now it's a collection of Dirac delta functions. And if I wanted to, I could try and convert this, use this to write down a discrete time signal, which is essentially equivalent to this this now continuous time signal that's made up entirely of delta functions. So what you should do is try to get familiar with the sampling property of the impulse function. Try to make up some new functions x of t in the previous examples that we saw. Try to make up a few more and change the location of the delta function and use the sifting property to evaluate the integral. And as you do that, you'll start to get a feel of how to work with these signals in the process of doing integrals. And later on, when we do convolutions, we'll see how this delta function can be used to make copies of signals.